I hope to show you what you think will be some very exciting results in this talk, collected too with the Evosep system. Let me just rearrange my windows here so I can see my presentation. Okay, so I want to start off by explaining what the timsTOF Pro is and what it does, and that requires explaining the concept of parallel accumulation serial fragmentation, which is based on our ion mobility separation front end. So the idea of PASEF was developed in collaboration with Matthias Mann and his student, now Professor Florian Meyer rather, at the Max Planck Institute. The concept was developed in 2015 in collaboration with Oliver Rather and Mel Park at Bruker, and we introduced it as the basis of the timsTOF Pro at HUPO in 2017. So the instrument's been on the market for a couple of years for DDA proteomics. And the way it works is shown in the figure on the right. So schematically, we have the exit of the desolvation capillary on the left. The ions pass through the TIMS tunnel, which is split into two. Then there's a quadrupole for selecting ions for fragmentation, followed by a collision cell for fragmenting them, and the QTOF analyzer. That's shown in a little more detail and more geometrically accurately on the bottom. In fact, the desolvation capillary axis is perpendicular to the ion beam axis. So we have a deflector plate here, which turns the ions onto the ion beam axis 90 degrees. And this TIMS tunnel, which is broken into two regions, consists of a series of plates with the same diameter hole in them. And those plates have RF on them, so they form an RF ion guide. And because we have high millibar regime pressure here at the exit of the desolvation capillary, where there's a lot of gas coming out, and 10 to the minus 4 millibar over here, there's a fairly high flow of gas from left to right as you're looking at the screen here. So high velocity of gas is indicated by these arrows from left to right. Now these plates that we have RF on are actually isolated with respect to DC, so we can put a potential gradient. And what happens as the ions enter this tunnel and start to go up this potential gradient, there's an increasing electric field gradient or potential pushing them against the gas flow. And when the force from the gas flow pushing them to the right is balanced by the force from the electric field pushing them to the left, they stop. The position at which they stop is determined by their size. The ions that are bigger feel more push from the gas and get pushed further up the potential hill. So this device is a way to separate things according to their collision cross-section or their ion mobility. The lowest ion mobility, highest sized ions end up near the exit, and the smallest ones end up at the beginning. And what we then do is scan this potential down and scan the ions out according to their size. From the voltage at which they elute, we can calculate, or using a calibration equation, we can determine their collision cross-sections, which is a fundamental property of the molecule. And then we measure their masses. And we scan this voltage typically when we're doing DDA proteomics down in the course of 100 milliseconds. The parallel accumulation part comes about because we have this broken up into two sections. So while we're scanning this voltage down, we're accumulating the next batch of ions over here. When this is all the way down and empty over here, we raise it again, transfer the next batch of ions, and scan them out. Now the serial fragmentation occurs because in the first scan, the first time we drop this potential, we measure their masses, and then we run a precursor selection engine over it, and we determine which ones we're going to fragment on the next 10 scans. So each of these takes 100 milliseconds. In each scan down on subsequent scans, we serially fragment the ions according to the selections made by the precursor selection engine. And that results in being able to do 10 to 15 ions per 100 milliseconds for 120 hertz sequencing speed. So parallel accumulation followed by serial fragmentation, that's the PASEF acronym, which gives us 120 hertz sequencing speed, all enabled by this TIMS separation. We call it 4D proteomics because the fourth dimension of information we get is the ion mobility or collision cross-section derived for each peptide. We measure tens of thousands of those in, say, a cell extract proteomics run. And the other beautiful thing that we get out of this is an additional layer of chromatographic focusing, shown over here. Ions that would have eluted continuously over 100 milliseconds now come out in tight focused packets that are only 5 milliseconds wide. So we get big bursts of signal in both MS and MSMS scans. And this has actually given us a 30x boost in sensitivity, where we used to inject 2 micrograms on our QTOFs. Now with the TIMS up front, we inject 200 nanograms. So the sensitivity boost comes from both the chromatographic focusing and the parallel accumulation, enabling us to use nearly 100% of the ions. So I like to think this is a real evolution in mass spectrometry. Anytime you say you can go faster and maintain your mass accuracy and your resolution and increase your sensitivity, I think it's a revolution, because all know that usually in mass spectrometry, if you want to go faster, you have to sacrifice something. Here we've actually improved everything. And this has been an exciting collaboration that we've continued to work with the group of Professor Mon on. Let's see, how do I get my slides to advance? There we go. And where we are now is that we can identify 6,000 protein groups and 60,000 peptides in a single run. And I want to emphasize the number of peptides. 60,000 peptides is really an impressive number in a single 100-minute gradient. We injected here 400 nanograms of an in-house prepared HeLa digest. And the speed is important to data completeness as well. You can see here the number of peptides that we identified is nearly constant across number of proteins that we identified is nearly constant across these 3 runs, between 6,050 and 6,100 peptides identified across these 3 runs with 1% FTI. At the peptide level, the data completeness is also very good, greater than 87%. 54,000 of these peptides were identified in all 3 runs for 87% data completeness at the peptide level. The other thing that we got out of this instrument is really a high robustness and throughput. So we believe that comes from the off-axis ion delivery. The ions, as I mentioned on 2 slides ago, are delivered perpendicular to the ion beam axis and deflected onto the ion beam axis. And that, together with the improved sensitivity, meaning that we load less sample, 200 to 400 nanograms maximum now, means that we keep our ion optics cleaner. And this is from a quote from a paper published in Molecular and Cellular Proteomics by Professor Mon and his coworkers in 2018, after they'd had the instrument for more than a year. And you can see that over the course of a year, this is showing the number of proteins identified from 200 nanograms of HeLa injected on column, and they're always above 5,000 proteins, except for these 3 occasions where they determined that was because they needed a column change. So this quality control metric easily tells you when you need a column change. Occasionally you might need to clean the front end capillary, but in the course of this year and even subsequent years since then, we've never had to clean beyond the front end of the instrument. We've never had to do a quadrupole cleaning or anything deeper in the ion optics. So this can also be tuned and calibrated in minutes, and this leads to the capability to run very large cohorts, hundreds of samples per day over days or weeks for clinical research projects, and totaling thousands of samples. And I'll show you some results or information on that later in the talk as well. The rest of the talk is going to focus on data that was acquired using a technique called dia-PASEF. So that's a flavor of PASEF that was developed as part of a collaboration between Matthias Mann and the group of Rudy Ebersold and the group of Hannes Roos at the University of Toronto. And as you all know, data-independent acquisition is an attempt to solve the data completeness problem by trying to fragment everything that's there. And dia-PASEF is just a unique way of doing that using PASEF that I'll explain on subsequent slides. It has unique features that we think make it a near ideal mass analyzer for shotgun proteomics. It has nearly 100% duty cycle, and it also has very high efficiency in fragmenting the precursors, up to 100%. And the trapped ion mobility separation will let you separate out the +1 ions, so you focus on your +2s and 3s, the higher charge states that are really interesting. And the 4-dimensional proteomics feature allows you to do alignment in additional dimensions. We align not only in retention time and mass, but also in mobility. And so that allows us to do more specific extraction from the libraries. Now, as I mentioned, PASEF was proposed in 2015, introduced in 2017, and then in 2018, Matthias and Rudy were talking and came up with this idea for a PASEF-based DIA approach. And basically, the idea there is that as you're scanning out the ions in mobility, you can also scan the quadrupole along with that and fragment mass mobility windows. And so our dia windows are not mass windows anymore, they're mass mobility boxes. And I'll show that in more detail in some slides. And that was introduced, first introduced as a concept at the HUPO in 2018. We continued to show work in progress at ASMS and HUPO in 2019, and we're releasing this as a full release at this year's virtual ASMS right now, with full GUI for setting up your workflows and full support by Skyline and other software packages, including Peaks and Biography's Spectrometer. So let me remind you what dia is. You probably all know that, but it's basically, you set up, you divide your mass range up into so-called windows. In this case, we're dividing a 400 mass unit range from 500 to 900 up into 20 mass unit wide windows. So when you're fragmenting the first window, ions in the first window, your quad is isolating those and basically throwing all these away. You do that for all the subsequent windows. So at any given time, you're fragmenting 5% of the ions. Now, eventually, as you step through this, you fragment all the ions that are there and you get good data completeness, but you're still not making the most efficient use possible of your ions because you're selecting windows. And dia schemes in general use 1 to 6% of the ions, depending on the width of the windows that you're using. The narrower the windows, the easier, the less complex the MSMS spectra is, the easier it is to pull your fragments out and correlate them with your precursors. But obviously, then you make less efficient use of your ions, and it takes longer per cycle. Let's look at what happens in dia-PASEF. In dia-PASEF, Rudy and Matthias noticed, well, as you're scanning out the ions as a function of mobility, you're also going down in mass. Mass and size are correlated. They're not completely the same, fortunately, so that gives us the ability to separate things and provide an additional dimension of information with the ion mobility, but they're correlated, and so we can set our windows, these are actually boxes now up, so that we fragment mass mobility boxes that are focused on the +2s and +3s as shown in the shaded region here. If you were just doing mass windows, you'd isolate everything in this box and you'd do it once. We can do 4 or more boxes depending on the complexity of the sample per PASEF scan, and so we can make much more efficient use of our ions. And this is a HeLa heat map that shows the ions as a function of mass, mobility, and you can see that we're using, in this case, we're using a total of 64 windows, I should say mass mobility boxes to cover the region of interest. But with that, we're using about 6% of the ions. If you use 64 windows in a real DIA experiment or without the TIMS front end, you would use only 1.25% of the ions. So we're at least in general 4 times better ion utilization is better than DIA and up to 100%. We're very selective to the ions of interest. We can set up our boxes so that we select the ions of interest, and we use that 4D feature alignment to pull out the ions of interest and achieve good data completeness as well as good qualitative and quantitative results. So here's some results. This shows HeLa extract and yeast extract. These are, again, 400 nanograms injected on column. The library had 105,000 peptides in it, generated from 24 fractions in the case of HeLa. And you can see we have 7,700 proteins extracted in a 90-minute run from the library, 97,000, more than 97,000 peptides. So really good coverage of the library with a 90-minute run. Still very good with a 60-minute run. With a 30-minute gradient, we're still getting what would be, have years past been considered very, very good results of 6,400 proteins identified and 59,000 peptides. And with yeast, this is again 48 fraction. In this case, it was a 48 fraction library, and we cover almost the entire yeast proteome at 90 minutes and 60 minutes. There's not much difference in the number of things we detect at 90 minutes and 60 minutes because the instrument's so fast and the yeast proteome is not that complex. And even at 30 minutes, we get good coverage. So these results are available, are shown on the poster at ASMS this year and as an application note, number 170 for Bruker. But can we do better? And so to do better, we talked to our friends at Evosep, Nikolai and the team, and we decided to go ahead and use the Evosep One, which has been developed to increase robustness while maintaining the sensitivity inherent to nanoflow LC running at 1 microliter per minute, so not extreme nanoflow to give you good robustness, and coupling that with the very high speed of the timsTOF Pro for the mass spectrometry, and the 4D feature alignment. So for these experiments, we generated a library with 24 fractions from Gila using the 60 sample per day. So this was all done, the library generation and the analysis were done on Evosep using Evosep standard methods. And then we did the DIA data with in triplicate using 100, 200, and 300 sample per day methods. And we also used direct DIA on that data to be able to generate a hybrid library containing the library from the 24 fractions plus the direct DIA library. The direct DIA library, the hybrid library approach allowed us to realign the retention time and use the 60 sample per day libraries for the shorter runs as well. So we had library generation on the 60 sample per day method resulted in a library with 8,381 protein groups with 93,000 peptides. And we did that in only 10 hours. So you can generate your libraries much faster as well and get very good coverage. What do the results look like? Well, we identified 5,200 proteins with the 60 sample per day method. That's, I believe, about a 40-minute gradient, so really good results. I want to highlight that we identified 40,000 or extracted 40,000 peptides from the library, so well over 50% of the library at that, or I should say almost 50% of the library at that speed. And impressively, even at, you can read the numbers yourself, but even at 300 sample per day, we're identifying 2,000 proteins and 10,000 peptides. It's really pretty amazing results. And again, I want to highlight the peptide numbers. And here I want to do a comparison with a paper that was recently published on an instrument using Thames with a compensation voltage of 45. And they showed that they could get significant improvement in the number of proteins I identify using Thames with 500 nanograms of fuel injected. This was the 60 sample per day method on the Evosep, but there were some custom aspects to this experiment. They used custom column and gradients using standard, as I said, methods available and column and consumables from Evosep. We were able to identify slightly more proteins, not a dramatic difference, 5,400 as opposed to 5,100. But I want to draw your attention to the CVs here. When they look at the number of CVs at 20% or less, they saw 3,600 proteins with CV of 20% or less. We have 4,300 proteins, and at 10% or less, we have 3,200, and they have 2,700. And again, that's why I emphasize the number of peptides here. We saw nearly 40,000 peptides. They saw on the order of 29,000 peptides in that paper. And you can also see that in the peak ID rate as a function of the gradient. At the peak of the gradient, we're extracting nearly 4,000 peptides per minute, whereas in their paper, they were extracting around 2,600 peptides per minute. So peptides are important. If you measure more peptides, you have the chance to measure more peptides per protein. You'll measure maybe the same peptide, extract it more often. You'll get better coverage of your protein and better CVs in your LFQ. And of course, there's other experiments where you're just interested in peptides like PTMs. If you get more peptides, you get more PTMs, peptidomics, immunopeptidomics, and uropeptidomics, which are interested in other peptides. So speed and peptides identified are important, and that's where I think the combination of the timsTOF Pro and the Evosep really excel. And also in terms of data completeness, the data completeness and CVs are very, very good. Here you can see the number of proteins goes across all three runs, increases from 5,200 to 5,300. So a very small increase if you add the proteins together, whereas the number of proteins seen in all three data sets is 4,900. So that really, really good completeness and very good CVs. 81% of the proteins can be identified with a CV below 20% and 65% with a CV below 10%. So Catherine Wang did a very large COVID-19 research project, which has been submitted. She did it very fast. And she said that as a result of her experience now with dia-PASEF, it's now the method of choice in her lab, and we're very much looking to see the results coming out of that. And I mentioned very high throughput work. Now, this was DDA experiments, but Roman Fisher recently did a 2,600 sample clinical cohort and 1,700 library and QC runs in the course of about a month, 4,300 MS runs with the 100 sample per day method on the Evosep. You can see this is a stack of boxes that were run over the course of that study. They cleaned the transfer tube once and used 3 columns and were able to compare the results over that entire study. And that work is also, the data analysis is in process and the publication is in process. And so, but we're very excited to see what can be done with studies like that in data independent analysis. So with that, I'd like to wrap it up, and you can read the conclusions yourself, but I think I've shown that we have this robustness combined with speed and sensitivity in 4 dimensions that really has a lot of promise for data independent analysis and short gradients together with the Evosep One. So thanks again to Nikolai, and I'll turn it over to the speaker.
Thank you very much, Gary, for a very nice talk. I think it's very exciting what can be done with these high-end mass spectrometers, the new mass specs that spearheading performance, and also in combination with short gradients, of course. So thank you very much for that very nice presentation. And if you have any questions for Gary, please put them in the chat box, and then we will address them at the end of the seminar. Gary will unfortunately have to leave, but I will do my best to address any questions that's for Gary. So let me just extend another warm welcome. Unfortunately, we had a little bit of a technical glitch in the beginning, so some of you may think that Gary was in the spotlight from the beginning. That was just because we didn't flick a very important button. Yeah, so basically that's what happens when you are doing a live webinar sometimes. But anyway, this is our second breakfast seminar at ASMS 2020. This is a seminar about our vendor collaborations, and we have always been vendor neutral at Evosep, and it's very important to us to really work with the leading mass spec vendors to see what our technology can do with the best of the best when it comes to mass specs. Just to give an introduction to Gary, we very early on, when we developed the Evosep One technology, realized that this timsTOF, and especially the passive technology, could do really wonders for the short gradients. And especially with the dia-PASEF that Gary just talked about, that was something that got us really excited. And I think with Gary and his team, the application team in Bremen, we managed to really pull off some of these data not so long ago. So really nice work. And once again, thank you very much for the nice presentation, Gary. So we also have a presentation from Emily Chen from the PMSC, Precision Medicine Center in Boston. And her talk is more about the plasma workflows. It's really about standardizing the workflow, making standardizing and make it more scalable. So we'll have her presentation in a second. And then at the end, we will have a very recent collaboration that we started with Agilent, where Dr. Linfeng Wu will give a presentation about targeted workflows using the triple quads, the Agilent triple quads. So back to Emily. So I'd like to present Emily Chen from the Precision Medicine Center in Boston. And I think it's been really nice to see what can be done in terms of putting workflows together. So Emily has been really focused on plasma workflows, trying to bring the sample prep, all the sample manipulation together into kind of one complete workflow. And I believe this is what her presentation today is about. So Emily Chen, thank you very much, and please.
Hello. Can you hear me?
Loud and clear.
Yeah. Can you see the slide?
Yes.
Just to confirm. Okay, great. Thank you, Nikolai, for the introduction. It was a great talk, also from the previous talk. Welcome to the 2020 ASMS Reboot Evosep Breakfast Seminar. I'm the Senior Director of the Thermo Fisher Precision Medicine Science Center. Today, I will switch the gear and talk about the concept of a complete workflow solution, not just about protein numbers. And I'll introduce the Thermo Fisher large-scale plasma protein profiling workflow in collaboration with the Evosep, which we have been working with, very nice group of people working the Evosep for in the past couple years or so, and also the workflow on our newest Explorers 240 mass spectrometer for plasma biomarker discovery. As we are moving away from the one-size-fits-all healthcare model and moving toward the patient-centric precision medicine concept, advances of a molecular profiling technology give us hope of achieving precision medicine. This is particularly true for the field of mass spectrometry. Although advances in the MS technology has shown great promises for translational studies, we also come to the realization that our dilemma to address and understand the biodiversity of a human patient using the existing MS-based proteomic technology. Accessible biofluids are essential for monitoring human health and diseases. Proteomic characterization of blood plasma is very important for clinical proteomics and particularly to biomarker discovery studies. The vast dynamic range and high complexity of plasma proteome, however, have proven to be serious challenges and have often led to the trade-off between the depth of coverage and sample throughput to obtain reproducibly quantifiable results. Discussions of analyzing human blood often involve in question of depleting or non-depleting abundant protein, sample throughput, how to quantify plasma protein, such as label-free, TMT labeling, DDA or DIA. To make matter more complex, we'll add the consideration of clinical relevance, which is very important for study design, and how to connect biomarker discovery with the assay development. It is important to consider throughput and quantification consistency when you choose the analytical workflow for biomarker discovery. How do you design the workflow to address the need of high throughput with the precision quantification and consistency for large-scale studies? First, sample preparation workflow needs to have a low variability because we are handling precious and limited human samples. Secondly, the ability to prepare a large number of samples simultaneously with a standardized method significantly reduces the sample prep batch effect. Third, high flow rate produces more robust LC performance for LC-MS analysis. The instrument robustness is also necessary as a part of the translational workflow solution. Last but not least, a robust workflow solution needs to have a proper QA/QC procedures that built in the workflow using standardized standards and also lockdown protocols. In this seminar, I want to introduce our ultra high throughput plasma protein profiling, or uHTPPP workflow. It consists of automated sample preparation, rapid LC gradient with the Evosep One system, and our newest addition to the Orbitrap Explorer mass spectrometry family, Explorer 240. With integrated 96-well EasyPap sample preparation kit and the automation script on the Hamilton liquid handling robotic system to digest plasma proteins and purify resulting peptides, the system costs less than $150,000 and less than $20 per sample for the consumables. To give you an example of the throughput, we can prepare 96 samples in 4 hours or 1,000 samples in 2 days. With automated Evotip loading and 60 runs a day throughput, data acquisition of 1,000 samples can be done in less than 18 days, including necessary system suitability runs. uHTPPP utilize optimized EasyPap 96-well MS sample preparation kit for digesting plasma and purifying the resulting peptides. 96-well samples and reagents from the sample prep kit can be loaded onto the Hamilton liquid handling robotic system, and an automation script will do the rest, including sample dilution, reagent distribution, peptide purification, and peptide drying. The entire process requires less than 5 minutes of hands-on time. As we can process 96 samples at a time, uHTPPP enables a rapid sample turnover and minimize the batch effect from sample preparation using a standardized method. Instead of protein identification, we optimize the automation script to maximize peptide recovery from samples and to minimize well-to-well and plate-to-plate variability. Here we show close to 90% of peptide recovery rate with less than 10% CV for well-to-well and plate-to-plate consistency. We're able to obtain less than 10% CV of peptide recovery rate from 3 plates of pool control serum. When apply uHTPPP sample prep to a patient cohort, we found around 20% CV from those patients' serum based on the equal volume, which we processed 125 samples in 2 plates. By measuring peptide concentration after peptide sample preparation, we're able to detect patient-to-patient variability before LC-MS analysis. With a consistent and high-throughput sample preparation, precise quantification can then be obtained by analyzing samples with high-throughput chromatography, for example, using the Evosep One LC system, and our newest Orbitrap Explorers 240 mass spectrometer for large-scale translational studies. Evosep One LC is an integrated peptide purification and separation liquid chromatography system. It uses disposable trap column to capture peptides and optimize gradient to reduce sample carryover and injection cycle overhead. It is an easy-to-operate and self-monitoring LC system that offers optimized plumbing and characterized methods, as well as the self-monitoring and self-calibration calibrating functions. And we're happy to share with you that in collaboration with the Evosep team, we introduced a newly optimized gradient for our Easy Spray ES806A column designed for plasma protein profiling. You can easily position the column in our Easy Spray ionization source with an integrated column heater. Here is a comparison of a chromatographic characteristics of the Evosep column, which is 8 centimeter column with 100 micron ID and 3 micrometers Reproducible C18. And the ES806 column, which is 15 centimeter with 150 micron ID and 2.2 micron C18 peptide resin. The figure on the left shows that the ES806 column yields sharper peaks as well as more consistent peaks across all PRTC peptides, spike in the plasma compared to the Evosep 8 centimeter column. The PRTC peptides are heavy peptide standards that you can purchase from peers and use to monitor LC retention time and the peak area consistency for the duration of your study. The figure on the right shows that ES806A column has more consistent PRTC peak areas than the Evosep column, especially for the early eluting hydrophilic peptides. The peak areas for most of the PRTC peptide on the ES806 column is less than 30% at CV. This year, we introduced the new Orbitrap Explorer 240 mass spectrometer for translational proteomics with the mature Orbitrap technology, leading performance, application versatility, and operational simplicity. It can handle peptides, intact proteins, and small molecule applications. It scans mass range from 40 to 6,000 mOV with improved selectivity for core isolation. It has maximal resolution of 240,000 at 200 mOV and excellent mass accuracy with external calibration and can be further improved by EVIC, internal calibration. Finally, it comes with optimized method templates for different applications that you can choose from your method editor, or you can compare with your own method. Here is an example of the study design we use to run control pool serum. We include 100 nanogram of HeLa digest lysate from the peers as the quality assurance run to monitor the system suitability. Both HeLa and depleted serum samples will spike in with the PRTC peptide standards to monitor the mass accuracy and the chromatographic stability. As expected from Orbitrap MS technology, we see less than 5% ppm mass accuracy stability for 5 consecutive days with only external calibration using the PRTC peptide standards, and less than 6% retention time shift over 100 injections with ES-A068 column on the Evosep LC. To determine the number of the detectable and quantifiable plasma proteins, we perform analysis on 2 different loading amounts and 2 different gradients using an ES-A068 column on the Evosep LC. By applying the spectral library search and feature mapping algorithm of the Proteome Discovery software, we reproducibly identify and quantify over 400 plasma proteins by loading 200 nanogram of top 14 depleted serum with either a 21-minute or 44-minute Evosep LC gradient on Explorer 240. We could detect and quantify around 500 plasma proteins by loading 500 nanogram of top 14 depleted serum and around 44 minutes of Evosep LC gradient on Explorer 240. In this data set, we saw more than 70% of proteins were quantified with less than 20% of CV across 150 injections, which supports the feasibility of delivering excellent and quantification reproducibility for large-scale studies with the newest ES-A06 Evosep LC gradients on Orbitrap Explorer 240. We understand and agree that it takes a village to discover biomarkers, and therefore it is important that we're able to provide consistent proteomic analysis among different instruments at a different times. So on the left, I want to show you our benchmark experiment from 4 different Explorer 240 at 3 different sites. Less than 3% of CV protein identification were observed from this multi-instrument benchmark study. For plasma protein quantification, we ran over 100 injections of plasma analysis with the same samples, but 5 weeks apart to show you the reproducibility of a quantitation. As you can see, both protein and peptide quantification were very, very consistent, even though the sample were run and analyzed in 4 weeks apart. I hope this seminar provides you with a workflow that can address the challenges of plasma protein profiling, tested with the real patient samples. Here is a quick summary of the benefit of applying our uHTPPP workflow solution. So it provides a rapid sample turnover and minimize the hands-on time, and therefore minimizing sample prep batch effect for large-scale studies. It has a built-in QC script, which I don't have time to talk about it today, but it can be utilized to verify the system before sample processing. It adopts a standardized protocol and template to facilitate robust output and report generation. The whole workflow has low accumulative effect errors to allow for exceptional quantification consistency. It is easy to implement and easy to scale up from this workflow. Finally, I want to leave you with some idea from studies that we and others have done to better understand the biodiversity of human plasma in different biological contexts using the Orbitrap technology. This is our study of using uHTPPP workflow to classify normal versus non-small cell lung cancer patients using 1 microliter of human plasma sample. In this study, they used the plasma protein profiling data to examine the inter and intra-individual, as well as the gender variability among different plasma proteins. Plasma biomarker can also be useful for diagnosis of infectious disease, such as multi-drug resistant tuberculosis. Potential biomarkers can be further analyzed by the biological function and connectivity of those proteins. With a large human cohort, here is 1,500 plasma protein and 8 plasma proteins. This study looked at dynamic changes of plasma protein for weight loss and maintenance at 4 different time points. This is a longitudinal study of biological process during the weight loss and maintenance. Now, we look forward to hear from you about what you can do with a consistent and reproducible analytical platform for plasma biomarker discovery. Lastly, I would like to acknowledge exceptional Thermo Fisher teams for remarkable effort to generate content I presented in the seminar today. Thank you for your attention and your participation in today's seminar. We look forward to your feedback and questions.
Thank you, Emily, for a very nice presentation. It's some really nice work, and I really think that it's so important that somebody takes up the challenge of putting these individual pieces of technology together into a complete and also standardized and scalable workflow. So, I mean, this is really how we take proteomics and put it into kind of a more clinical setting. So it's a great work and a really nice presentation. Thank you very much.
Thank you.
So our last speaker of the day is Linfeng Wu from Agilent. And we started the collaboration with Agilent about a year ago, I think. And it was kind of talking a little bit back and forth, kind of would it work, would it not work, how well would it work with kind of Agilent technology. And at some point we decided that why not try it out. So I had the pleasure to visit Linfeng in Santa Clara. And the idea was that we would just try and set up an instrument and see what we could do. So we had a pretty ambitious plan that Linfeng will talk about. But since then, I mean, we really kind of saw that the technology worked really well together. And I think, I mean, it's always working kind of in a nanoflow regime. Does it work? How well is the source? Is the source going to be compatible with kind of, you know, the Evosep technology and all this? And what we found was really kind of, it just worked really, really well. It worked out of the box. We had a great time. We acquired some nice data. And just today, we have announced a co-marketing agreement with Agilent. So I think there's a lot more to come in the future. But now I think I would give the word to Linfeng and let her do a presentation about the work that we did. So without further ado, hello, Linfeng. The word is all yours. Linfeng, you are self-muted, so you need to unmute yourself. Sorry.
Okay.
Perfect.
Okay, can you see my screen now?
And also speed. Everything is good. Thank you very much.
Okay, thank you, Nicolai. And first, I would like to thank you for inviting me to present our work on protein quantification in plasma using Evosep One and Agilent 6495 triple quadrupole LC-MS. So, as many of you have know that in the recent trends in translational research, people like to focus on multi-omics, including genomics, epigenomics, transcriptome, and proteomics, and metabolomics, and their relationship with each other and with the environment. And the expression of this multi-omics on organisms produce phenotypes. And today, our topic is targeted proteomics. So for biomarker evaluation and precision medicines, a lot of time people need to measure the protein abundance in a larger cohort and follow their change during a time course. This type of experiment design easily ends up with hundreds and even thousands of biological samples. So typically for this kind of experiments, reproducibility and robustness is top things people will think about. This will require very high reproducible and robustness analytical instruments. And to achieve this goal, typically standard flow LC-MS is a better choice than nanoflow and microflow LC-MS. And Agilent 6495 triple quadrupole LC-MS coupled with the jet stream source has been well accepted by the market for targeted proteomics. But sometimes researchers cannot get enough samples, so they only have a very limited amount of samples. So this is the reason why we would like to evaluate Evosep One coupled with Agilent 6495 triple quadrupole to complement our current standard flow LC-MS system. So here is the MS platform setup used for this presentation. It combines Evosep One with Agilent nano spray source and Agilent 6495 triple quadrupole LCMS. On the bottom shows the nano spray video capture. If you can see, there's a very faint spray, and it can nicely. This spray is very robust, and in the middle is needle holder. This is a clamshell. It connects the analytical column and the stainless needle. Evosep provide us the analytical column and the spray needle. It fits nicely together on in the Agilent clamshell. So we would like to evaluate this platform and evaluate their robustness, reproducibility, and sensitivity for targeted proteomics. So to do that, we took a raw human plasma and first diluted the plasma with ammonium bicarbonate, and then we denatured, reduce, and alkylate the samples, and then use trypsin digest the sample. And then we directly dry down the sample without any cleaning steps. And then we reconstitute the sample and spiking with the stable isotope labeled peptide standard mixtures. And this standard peptide mixtures purchased from MRM Proteomics. It's a peptide quant biomarker assessment kits, and the standard peptide are balanced has equally amount in these mixtures. We're spiking these standards into the human plasma digest and use dynamic MRM to monitor 33 pairs of heavy and endogenous peptides levels. And we designed 3 experiments. First experiment, we spiked the standards in plasma at 8 concentrations, and we loaded this 8 concentration sample on the Evo chips with replicates. We actually prepare 10 replicates, and we rerun the 5 replicates first, and to produce the standard curves. And then we prepare another samples. And the remaining 5 replicates from the standard calibration samples we stored in 4 degrees for later use for later experiments. And for the second experiment, we prepare a sample. A large amount of human plasma digest was spiked with heavy peptides at 10 femtomole per microgram. We keep injecting these samples. We inject 574 samples for robustness test. And after the robustness test on the same columns, we took the remaining calibration sample, run the standard curve analysis again. So then we can compare the standard curves before and after robustness test. So before I show the data, I would like to highlight a few things regarding the LCMS used for these experiments. We use an analytical column. This is an 8 centimeter column with 100 micron ID packed with 3 micron C18Bs, and the LC flow rate is 1 microliter per minute. We use the LC method. It allows us to run the 60 samples per day. And in this dynamic MRM method, there's a total of 198 transitions, which map to 33 pairs of heavy and light peptides. So this gave us 3 transitions per peptides. So the whole experiment takes about 12 days consecutive operation, including the method development on the first day and also the 3 experiments. And for the 3 experiments, a total of 654 samples were injected. For each injection, we load 1 microgram plasma digest on column. So during this whole process, there's no column change, and there's no any adjustment on the LCMS system. So the spray needle was not changed, and the spray voltage was not changed, and the instrument was not tuned or clean. So for convenience, I would like to show the robustness test data first. And here shows the peptide retention time distributions for all the targeted peptides. So there's a total of 574 replicate injection. So here, different color represent different peptides. And throughout this whole robustness test, we see the retention time pretty much keep consistent. There's only very small bumps in the middle. This means that the back pressure of the analytical column was not increased during this whole process. So and next, let's look at the peak area relative standard deviation. This distribution histogram shows the ISD distribution. A median of 8.5% of ISD was achieved for all the peptides, and for almost 94% of peptides, their ISD is below 16%. We only observe 2 pairs of peptides which have a relatively higher ISD, and then we look at what caused this high ISD. One pair of peptides, we found that this is unstable because we observed more than 50% degradation after overnight storage in the refrigerator, in the solution. And the second pairs of peptides, we observed a very severe background matrix interference. So we have to manually integrate this peptide, and the manual integration caused a lot of variations. So they would conclude that the overall LCMS platform are very robust. And here I would like to mention that the ISD here shown here actually coming from 2 resources. One resource is from the manually sample loading process on the Evosep, and the second resource is coming from the LCMS platform variation. And here shows the 4 selected peptide, their raw MRM peak area distribution during this robustness test. We different color from different peptides. The peak area of the top peptides has about 11 folds of the peak. They have almost 11 folds response compared to the bottom peptide shown here. So the peak area ISD for these 4 peptides ranging from 6% to 7.9%. Their ISD, their retention time ISD ranging from 0.59% to 1.04%. And for all the peptide, all the targeted peptide, their retention time ranging from 0.5% to 2.8%. And most of the peptide actually have a ISD lower than 2%. So next, I would like to show the standard curve comparison run before and after analytical after the robustness test on the same column. So here shows one example peptide. This peptide coming from complement C3 protein in human plasma. And this is one of the well-responsive peptides. The calibration curve range from 4 atmol to 100 femtomole on column with 1 microgram human plasma also on column as the matrix. And you can see the standard curve run before robustness test and after robustness test are very similar. Their R squared are close to 0.999, and both standard curve have a lower limit of quantification 10 atmol on column. So here LLOQ was determined by the lowest spiking level with the ISD lower than 15% and their quantification accuracy between 80 to 120%. So if you have a close look of this calibration curve precision and accuracy, here on the left are the MRI chromatogram run before and after robustness test in 4 samples, including the matrix blank, 4 atmol on column, 10 atmol on column, and 20 atmol on column. You can see even at these low levels, we can detect a very nice peak for quantifications. And on the right is the ISD at the quantification for each levels. We can observe a very nice ISD and quantification accuracy across all the levels tested, even at the LOD and LOQ levels. So with this result, we conclude that this LCMS platform gave us very reproducible LC retention time for all targeted peptides across over 650 injections on a single analytical column. And the mRNA signal response showed outstanding stability during consecutive operation using complex plasma samples. And we don't need to do any adjustment on the LCMS. And very similar, the standard curve were achieved using isotope labeled peptides before and after robustness test. And we also observed that the sample storage, storage of sample loaded on the Evotips are very stable, because we prepared all the samples and loaded on the Evotip before our experiment, and they store the remaining samples in refrigerator for more than 10 days. So at the end, I would like to thank our Agilent teams and our collaborators from Evosep, and they are Chris Miller, Patrick, and Paul from Agilent, also Nikolai, Dotet, Jakob, and Ole from Evosep. And with that, I would like to thank you for your time. And I hope I have shown something useful for your lab, and welcome to ask questions.
Thank you very much, Linfeng, for a very nice presentation. I really think that, to me, the most exciting piece of data, although everything is exciting, but the most important piece of data was really how well the samples stored on the Evotip. It's one of these things that we have been kind of arguing. We have bits and pieces of data, but this at the time, this was the best quantitative data set that we have ever had on kind of how well peptides are stored on Evotips. So, yeah. But there's a lot of other really nice and great observations, but to me, that was something that I've been looking for a long time. Mm-hmm. So yeah. If you have any questions for Linfeng, Gary, or Emily, please put them in the chat box. And then let me again extend a very warm thanks to all the different instrument vendors, Agilent, Thermo, and Bruker, for these ongoing collaborations. It's really important for Evosep to be part of these collaborations, really engaged and trying to push technology. At least this is what really motivates this team here in Odense, is being part of spearheading the technology and making a difference to how what can be done with this technology. So let me see if there's any questions. Yeah, the first question is that's for Emily. Is Emily? Yes. Hello, Emily. So is the entire workflow that you presented today, is that commercially available?
Yes, it's entirely available. That you can purchase basically the sample preparation portion, the robotics with the sample preparation kit from Pierce. It's all integrated. Evosep and mass spec and software entirely, yeah, okay. Can be purchased.
Perfect. And I know that you also have made an application note about this. So basically, the entire recipe of how to get this going is available. Perfect. Okay. Then this is a question for Gary. And this is more for the high throughput. So, what the question is? What is the main advantage of the reproducibility that you're seeing in the data sets? So, I guess this is alluding to Gary mentioning that the reproducibility of the dia-PASEF was really nice, and the CVs was very low. Unfortunately, as I said earlier, Gary had to leave. But my take on this is two things. I think the dia-PASEF and the dia technologies in general have really improved a lot. But also having the more robust chromatography really allows to take full advantage. And I think this is what adds to the reproducibility in these data sets. And then I have for Agilent. Hang on a sec. Okay, so the question is for Agilent, so that's for you, Linfeng. How did you prevent drying out of the Evotips during the 4 degree stability test?
Okay, so actually I put a liquid in the plate, the sample Evotip the plate. So the top of the tip actually soak in the buffer A, the LC buffer A. So they are not dry out through this almost 2 weeks experiments.
Yes, and I guess I can allude a little bit on this. It's super important that the Evotips they don't dry out during storage, and if they are to be stored for a longer period of time, we really highly recommend to do it in the fridge at 4 degrees, and then add, as Linfeng said, add a little bit of liquid in the bottom of the box. That will keep them wet, and they'll store really well for longer periods of time. I think the longest we have done is, I know that we've done at least more than a month, but it still works really nice. I'm unsure how much more than a month we've done, but I think that's more than enough for us at least. Yeah, I think that's pretty much it. So basically, this is the last chance for putting in a question. I'm sure if you have other questions, either for us or for Emily or Linfeng, you are more than welcome to contact them directly. So please do so. And please also join us at, we have a virtual booth on Thursday. So it's on the screen now, you can see it. And here we will do a little bit more. We'll talk about our Evosep Plus, which is our big launch this year, and also our updated standard methods. And it was also a chance for you to engage and start a discussion if there's any topics that you want to discuss with us. So check that out on Thursday. If there's no more questions, I would like once again to thank both of you and also Gary, even though he had to leave, for contributing here, and also our very nice collaborations. So thank you very much, guys. Have a wonderful day, and hopefully see you on Thursday.